In this case, the bar has an angle theta. Let's imagine that theta is known and the length of the bar, L, is known. If we know alpha, we can deduce theta. And then same problem. Let's imagine that the mass is also known. The system is at static equilibrium. So we're looking for all the external force acting on the orange bar. In this case, it's actually simpler. We have a tension, which is horizontal, acting at C. We have the weight, which acts at the center of mass of the bar, and at the support, which is point A. Again, we're going to have to consider the normal force and the static friction, which is up. All right. For the fun of it, and just to practice, let's pick the usual coordinate system, but let's position it at C, just so that we can practice our torque again. All right. Static equilibrium tells us that sum of the forces is equal to 0. Let's just set that up, chapter 5, chapter 2. T is negative in the x direction, N is positive, and that's it. And in the y, Fs is positive, Mg is negative. So very, very trivial. No sine, no cosine. 30 seconds each. Again, we know M, but we don't know N, we don't know T, we don't know Fs, so we need one more equation. So let's calculate the sum of the torque at C. Obviously, we do not have to consider the torque due to the force T, because T acts on C, but we have to calculate the torque due to the 3 other forces. However, Fs and N act at the same point. Therefore, they share the same position vector. Hence, we can combine them into the same matrix. So really, we only have 2 matrices to consider. One for the torque due to the weight, and then one for the torque due to Fs and N, because they act at the same point. Therefore, we can combine those 2 matrices into one. Let's do the easy part. Mg in computation is from above, negative Mg, 0, 0. And then Fs and N, again, we'll grab it from the above 2 equation. Fs is positive in the y, N is positive in the x. So really, all we have to do is figure out the position vector. Position vector for the first, or the torque due to the weight, is from point C to wherever the weight is applied. So that's L divided by 2. Cosine alpha negative, and sine alpha also negative, because this is this position vector, which can be decomposed as the x and the y. So both should be negative. The x is the adjacent of alpha, therefore cosine. The 1 is the opposite to alpha, therefore sine. And then for Fs and N, it's obviously double that. Therefore L cosine alpha and L sin alpha. That's it. Let's evaluate those 2 determinants. First one will give us negative Mg times negative again times L 2 cosine alpha, okay, plus 0. The next one is going to give us negative L cosine alpha Fsk, and then positive N L sin alpha k. And that's equal to 0k. Be careful on that one. This times this is indeed negative, but as you turn around, you have an extra negative sign, which will cancel the negative sign due to the product of this and this. So the second term is positive, which means that the torque to Fs tends to produce a clockwise torque, while at the same time, the torque due to N tends to create a torque which is clockwise about point C. Again, K is everywhere. We can nuke it. What else is coming? L is coming. Yep. So really, we didn't even care about the length L. What we have left is mg cosine alpha divided by 2 minus fs cosine alpha plus n sin alpha. That's our third equation. 2 and 1. So again, we're back to a 3 by 3.